All right. So where we left off, we've got basically just the 2 chapters remaining. So we're currently going through NP, P, NP completeness, and reductions between problems, search problems. And then the last section of the course is called coping with NP completeness, which basically is, okay, you encounter a hard problem, still many times you have to try and solve it, right? Like, I mean, a classic example of a hard problem is you are a UPS, you have a set of packages you want to deliver, and you want to find the shortest path that delivers all the packages to people's homes. That's an NP hard problem, NP complete problem in its decision version. But it doesn't make sense for UPS to say, okay, that's a hard problem, let's forget about it, let's not do it. You know, like, I mean, they have to solve it anyway. So the question then is, how do you try and solve these hard problems? And so in the last week, next week, we'll go through some just high level ideas on how you solve these problems when they're hard. What we were doing last class was we were going through our first kind of reduction, right? Which was 2 problems that seemed very similar. One is Hamiltonian cycle. So you're given an undirected graph and you want to know, does there exist a cycle that passes through each vertex exactly once? Hamiltonian ST path was just a variant of this problem. So I'm given a start vertex, I'm given a goal vertex in my undirected graph, and I want to know, is there a path from S to T that visits each vertex exactly once? And our reduction, we were drawing it out in the form of a reduction. Remember, a reduction really is these 2 functions, f and h. F takes in a problem instance of your source problem and converts it to a problem instance of your destination problem. And then H takes a solution of your destination problem and converts it back into a solution to your origin problem, right? The one you started with. And so that's exactly what you can see happening here, where we start with an instance of Hamiltonian ST path. We convert it into an instance G prime of Hamiltonian cycle. We call our Hamiltonian cycle solver. If it finds a solution, we then use that solution to create a solution for our input instance. And if it finds no solution, we just pass that out and we say that there's no solution to our input instance. And so that pink box then gives us a solver for Hamiltonian path, right? And inside that box contains our reduction, which is these functions f and h, along with our Hamiltonian cycle solver. And our reduction was really simple. It was just given an input of Hamiltonian ST path. That's like this red graph here. All I do is I add another vertex x, and I add 2 edges, one from S to X and one from X to T. I then compute the Hamiltonian cycle on that graph, red plus blue. And if it finds a path, I just delete the 2 blue edges and I claim I'm left with a path. If it finds a cycle, I delete the 2 blue edges and I'm left with a path from S to T that visits everything. And if it doesn't find a cycle, then I claim there is no path. So let's now just go through those 2 arguments, right? We have to, when you think about verifying the reduction, you have to verify both ends of the output, right? That if it finds a path, then that path is correct. That's this top one. And if it doesn't find a path, then there is no path to the original problem, right? Or if it doesn't find a solution, then there is no solution to the original problem. That's what I mean to say. So is this reduction valid? And we'll go through the 2 cases. They're both pretty easy in this case. So one, sorry, I hit my, oh, come on. Here, let me try and move it this way. My arm's touching it, which just seems to be upsetting it. So, okay. So one, if Hamiltonian cycle has a solution, Then we want to show that Hamiltonian path had a solution. Did it just flicker again? All right, hopefully. I'm not doing anything different than before, but since X has only two neighbors, S and T, the Hamiltonian cycle must contain the edges, well, I'll write it, S to X and X to T, one after the other. Right? It's the only way to get out to X, the new vertex that I added. Deleting those two edges, SX and XT, gives a Hamiltonian path from S to T. Right, because it was a cycle. I deleted two edges that appear one after another in that cycle. So I've just broken that connection between S and T then, and also taken X out. And so now what's left must be the cycle or the path that takes me between S and T. Two is if HC has no solution, then I want to show that HP has no solution. There's a little trick in logic that I can use here, that what I'm trying to show right now is not HC implies not HP, right? No Hamiltonian cycle implies no Hamiltonian path. If I'm trying to prove that, I can instead prove the contrapositive. I don't know if you've heard this term, which is to reverse the direction of my implication and negate both sides. So rather than showing not HC implies not HP, I would show HP implies HC. Right? Reverse the direction of the arrow and negate what's on the either end of the arrow. And they're equivalent statements. So aside, it's the contrapositive. If I want to show P implies Q, it's equivalent to not Q implies not P. Right, that symbol there is not. So instead, I can just show if there's a Hamiltonian path, then there must be a Hamiltonian cycle in my constructed graph. So instead, show if G has an HP, then G prime has a Hamiltonian cycle. But that's kind of obvious, right? If I had a Hamiltonian path from S to T, just add in those extra two edges, S to X and X to T, and that then makes a cycle, right? Like just going back up to my picture, this one here. Right? If I already had a path from S to T, then I can just close the cycle by adding in the two blue edges, right? And now I've got a Hamiltonian cycle in my graph that includes the new edge or new vertex X. Is it still flickering or does it seem to be stable now? All right, good. Because when I'm looking down, I can't see that. So just take the Hamiltonian path, oops, plus the edges, s to x and x to t. And that forms a Hamiltonian cycle. Anyone confused by this contrapositive thing? Or does it make sense to? Trying to think of like a nice relatable example. Maybe, okay, I don't know if these help or these just are stupid, but let's say, for example, it's like I have an implication that says, if I'm tired, I go to bed. Right? Anytime I'm tired, I go to bed. Like that's the way it works. So then the contrapositive is, if I'm not in bed, then I'm not tired. Okay, all right, yeah. It takes a minute to process, but I think I don't know, for me, sometimes these like simple word examples sort of help to, like, but anyway, it's like a standard proof technique. Like if you take a math class, like in real analysis or something, you'll use these types of things. And often it's helpful when you have like knots in the thing you're trying to prove, because then you can get rid of them by looking at the contrapositive, right? We were trying to show not something implies not something. And so if you take the contrapositive, all of a sudden we take not, and the knots are gone. The double knot becomes no knot at all, if that makes sense. Okay, and then the last thing we have to do, so now we have this reduction. We've proved that it's correct. We also have to prove that the functions f and h run in polynomial time for the reduction to be valid. But in this case, it's kind of a trivial, I hope you agree with me that this is true. If we look at what the function f does, it takes in our graph and it adds a vertex and two edges. That can be done in polynomial time, right? I just copy over the graph, add an extra row to my adjacency list, and add two entries into it, right? Like definitely polynomial time. And then the h function, all I do is I delete two edges from my solution. So again, I can do that in polynomial time, just loop through the list of edges in the solution and delete two of them. So in this case, it's kind of holds very straightforward. F, it maps me from G to G prime. Just add a vertex and two edges. Give it a check mark. And H, which takes my Hamiltonian cycle and converts it to a Hamiltonian path. Just delete two edges. Oops. Okay, so we've shown that Hamiltonian cycle reduces to Hamiltonian path. We can also show the other direction. Oh, sorry, we showed that Hamiltonian path reduces to Hamiltonian cycle, didn't we? That's the way we went. We started with Hamiltonian path and we went to Hamiltonian cycle. We can show the reverse, which is that Hamiltonian cycle reduces to Hamiltonian path. And with that pair of reductions, it's like either problem could be used to solve the other in polynomial time. Either a solution for either problem could be used to solve the other. It's a statement in complexity theory that those two problems are essentially equivalent. And so if you have a reduction both ways between two problems, we say the two problems are in some sense equivalent. Yeah. Because, so the question was, why are we deleting the vertex X? Oh, why aren't we? We should. Yeah, sorry. Just delete two edges and a vertex. Thank you. Yeah. I just didn't finish my thought. You're totally right. Yeah. I guess it also depends how you store the solution. If the solution is just a list of edges, then you would just delete two edges from it. But if it's a sequence of edge, vertex, then we should delete two edges and a vertex. So this is a really straightforward reduction. Let me just repeat like the components of a reduction, right? You don't have to really explicitly write out this figure every time, but you do have to fill in the key components of it, right? Which is make an F, make an H, verify both the outputs are correct, and then give an argument as to why both F and H run in polynomial time. All those things are required to have a correct reduction. You don't have to go into painstaking detail into why it runs in polynomial time if it's like very clear it does. You know, like if it's just like, oh, create a copy of the graph and put edges or put edge costs that are 2 times the ones in the input or something. You know, you can say this runs in polynomial time since I'm just copying the graph. Like you don't have to like analyze it line by line. But we have to argue that it's polynomial time. So there's a bunch of reductions, and we're going to go through a few of them. Some of them are much harder to show than others. But here's just some reductions. All of NP, so any problem in NP, can be reduced to SAT. Actually, I'm going to draw it slightly different. All of NP can be reduced to circuit SAT, which can be reduced to SAT. SAT can be reduced to 3-SAT. 3-SAT can be reduced to a problem called 3D matching. 3D matching can be reduced to 0-1 equations. 0-1 equations can be reduced to a problem called subset sum. 0-1 equations can also be reduced to integer linear programming. Can also be reduced to Hamiltonian cycle. And it can even be reduced to, or sorry, I'll go this way. Hamiltonian cycle can be reduced to TSP. And there are actually arrows going the other direction for all of these as well. So another one that we're going to show is that, TSP, or sorry, is that SAT, for example, we're going to show can be reduced to TSP. Not quite, we'll actually do, we'll reduce it to directed Hamiltonian cycle, but that will then give a reduction between those ones. And so actually between any pair of these, there's a reduction. These are all NP complete problems. And we can say, and to establish that, remember, NP complete is the class of all problems, or a problem is in NP complete, let me say, if it's in NP and all other problems in NP reduce to it. So somehow we have to make an argument that there is a problem such that if I take any problem in NP, I can create a reduction from that problem to this one I've chosen. Our chosen problem is going to be circuit SAT. That's the one we're going to show. I'm also going to show you how circuit SAT reduces to SAT. And I'm actually also going to show you how SAT reduces to TSP. So that means like now that TSP, every problem in MP can be reduced to TSP. Also, every problem in MP can be reduced to subset sum and everything. It's just some of them are a bit easier to construct than the other. But let's go through a few reductions of increasing difficulty. Yeah. Yes. Yeah. So the question was, does every problem in NP complete reduce to each other? And the answer is yes. They all reduce to one another. Okay. And oh, sorry. I'm going to go. So we had a few reductions. Sorry, I was in the section of notes from last week because we didn't quite finish the ones I'd posted. So now I'm switching into writing a new set of notes. So let's do the reduction from Hamiltonian cycle to TSP. This again is not too complicated of a reduction. So I'm given an instance of Hamiltonian cycle, and I want to solve it with a TSP solver. That's basically what I'm trying to do, right? Hamiltonian cycle does not have edge lengths, right? It's just I get a graph, and I have to find if a cycle exists. In TSP, I'm given a complete graph. There's an edge between every pair of vertices. I'm given lengths on the edges. And I ask, does there exist a tour in that graph with cost less than or equal to my budget? So how do I go between these two? One thing you can think, right? Of course, the input I'm given, which is Hamiltonian cycle, isn't a complete graph. So I'm going to have to complete the graph. I got to add in all the other edges. And then my idea is going to be kind of simple. What if I just I'm trying to take an Hamiltonian cycle instance, the not complete graph, and make it a complete graph. What if I make the edges that are in the Hamiltonian cycle instance have lower cost than the ones that aren't? Then my TSP solver would prefer to use the ones with lower cost, right? Like the ones that are actually in the Hamiltonian cycle instance. And as long as I set my budget appropriately, I should be able to set it so that either it finds a solution that only uses the edges in the Hamiltonian cycle input, or it can't find one, in which case it uses one of the edges that wasn't in the Hamiltonian cycle input. Those have higher cost, right? And then it can't satisfy my budget. And so that's the construction I'm going to go with. So I'm given an instance G equals VE of Hamiltonian cycle, and I need to construct a TSP instance that consists of a complete graph, edge lengths, and a budget. And so what I'm going to do is the vertex set V prime is just going to be the same. I don't need to add any new vertices. So vertex set V prime just equals V. Edge set, I need a complete edge set. So it's going to be every edge UV, where U and V are in E. And then my lengths, I'm just going to do LUV, the length of the edge from U to V, is, let's call it 1, if UV is in E. So this is the Hamiltonian cycle edge set, right? Not E prime, which is the one I'm making. So it costs 1 if it's in the input graph, and it costs something more. For right now, I'm just going to write it 1 plus alpha if UV is not in E. where alpha is just going to be a positive number. And then what should my budget be? How many edges are on a cycle that goes through every vertex? Did you say? It's actually V, right? Because it's closed. So to do 3 vertices, I have to do 3 edges like the triangle, right? So budget. I'm going to make my budget exactly V. Cardinality of V, right? So either to solve this TSP instance, I have to find a tour that only uses length 1 edges because it has to use V edges. Otherwise, it's going to have a cost of at least V plus alpha, where alpha is positive. So if G contains a Hamiltonian cycle, then the same cycle is a solution to the TSP on G prime. Right, that Hamiltonian cycle uses only the length 1 edges. It has exactly V of them, so it meets the budget in my TSP instance. If, on the other hand, G does not contain a Hamiltonian cycle, then any tour in G prime must use at least 1 edge of length 1 plus alpha, and so tour has a length of greater than or equal to V plus alpha, which does not satisfy the budget. Therefore, no TSP solution. Right, so we have these 2 cases. G contains a Hamiltonian cycle, then TSP contains a solution. If G does not have a Hamiltonian cycle, then there's no TSP solution. Yeah. So, yeah, sure. So G, the question was what's different between G and G prime. So G was the Hamiltonian cycle graph. It's just an undirected graph that doesn't necessarily have all the edges. G prime is a TSP instance. So it's a complete graph along with edge lengths on every single edge. So is that make sense, or? Well, the thing we're checking in G prime definitely has a Hamiltonian cycle, because when you have a complete graph, you can always find a cycle that visits all the vertices. The question we're asking though in G prime is there a tour with cost less than or equal to B? Yeah. So just as like a picture, right? An input instance of Hamiltonian cycle might be like this. Trying to draw something different. Yeah.
So the second line you wrote there, could it be
Oh, yeah, sorry. Yeah, thank you. Yeah, the U and V here should be in V or V prime. Right, it's the same V and V prime, but yes, thanks. Right, so the Hamiltonian cycle instance could be this red graph, right? And I ask, does there exist a cycle that visits each vertex exactly once? I think the answer is no in that one, right? And so then to complete that, to make it an instance of Hamiltonian, of TSP, I'm gonna add all these extra edges. Right, and I put a cost of 1 on all these ones. And on all these ones, I put a higher cost, 1 plus alpha. Right, I think I'm just probably missing some blue edges. There should be a ton of them all the way across as well, and so on, right? And then I say, does there exist a tour on that red and blue graph that uses only red edges, basically, is what I'm asking. And then you can kind of see it's equivalent to the Hamiltonian cycle instance. Now, I left this alpha free, right? I didn't say what it was. I didn't assign it a number. You can actually get a few more results by playing with that alpha number. So one that is kind of interesting is if I set alpha equal to 1, so sorry, maybe just the last thing to say is I'm going to say that this completes the reduction. I should also argue that both F and H run in polynomial time. I think this is a case where it's fairly obvious, right? I mean, in a proof you're giving, you should write a line where you explain, right? Or at least say both F and H run in polynomial time. Here, all I'm doing is you can think I create a copy of the graph, add some extra edges, and define some edge lengths, right? But that all runs polynomial in the graph input. And then for the output, I don't really have to do anything, right? I solve my TSP instance, and that tour is the solution to my Hamiltonian cycle. Or if none comes out, then I say no solution exists. So now, if I set alpha equal to 1, then all edge lengths are either 1 or 2. These edge lengths satisfy something called the triangle inequality. Triangle inequality, which says that the length of the edge from I to J plus the length of the edge from J to K has to be greater than or equal to the length of the edge that goes directly from I to K. So the picture looks, right, you just have 3 vertices, I, J, K, and you have these edges. And the triangle inequality says that it's always cheaper or no more expensive to go directly from I to K than to get there via another vertex, via J. So yeah, this has to cost more than just going direct. And then you can see that this would then prove that Hamiltonian cycle also reduces to TSP with the triangle inequality. Because now I've created an instance of TSP that satisfies triangle inequality. So this might not be interesting to you, but there's people think, TSP with triangle inequality, that's a more relevant instance. That's what most real world instances will look like. And so you could ask, is it still hard if I have the triangle inequality? Maybe it's only hard when I think of weird instances that don't satisfy it. But then this shows, even with triangle inequality, I can still reduce from Hamiltonian cycle to TSP. Meaning it kind of gets no easier when I add in the restriction that I satisfy the triangle inequality. So Hamiltonian cycle reduces to TSP with triangle inequality. And since Hamiltonian cycle is NP complete, so is TSP with triangle inequality. Okay. So that's another like not too difficult reduction, right? The problems looked pretty similar. They're both finding a cycle and a graph. The only difference is whether the graph is complete or not and whether it have edge lengths or not. The next one I want to give, which we'll do after the break, is a considerably more complicated reduction. And it's not with the expectation that you could do this on your own. I mean, I couldn't do it on my own either. It's more to show you like how complex these reductions can get and some of the interesting ideas that people have come up with to create reductions. So let's take a 5-minute break and then we'll resume. Okay, so this example, just I said it already, but I just want to emphasize, I don't expect you to be able to do something this complicated, especially not like on a final exam or something like that. I just want to give you an example of like a pretty neat reduction that shows how we can relate seemingly very different problems. That's the goal of this, right? Because the two problems we're going to take is SAT, and then the other is Hamiltonian cycle. But I'm going to do directed Hamiltonian cycle because it's easier to use directed edges in this reduction. But you can think like if you just think quickly right now, these two problems do not seem very related, right? One is I have a Boolean formula and I'm assigning true false to it. The other is I'm given a graph, in this case with directed edges, and I want to find a cycle in that graph, right? That visits every vertex exactly once. So given a solver for this Hamiltonian cycle instance, how on earth am I going to solve a SAT formula? I think not clear. Unless you've seen this before, it's not at all obvious how to do such a thing. So let me go through the construction. It's kind of neat, and maybe it kind of opens your mind a bit to like more creative ways we can relate two problems to one another than what we've talked about before. So first of all, let's take in what's a SAT formula? We already talked about it, but it has a set of clauses. I'm going to call the clauses Z1 through Zm, and each clause has the variables, right? X1 through Xn. And let's say our SAT formula is in conjunctive normal form. So we have an and between each clause, and in the clauses we have ors, right? There's variables or their negation in each clause, and it's all ors between them. So an example could be something like X1 or X2 or not X3, that's one clause, and X4 or not X1 or X2. Right, so this is the clause Z1, this is the clause Z2. And what I'm going to do is I'm going to construct a graph G such that G contains a directed Hamiltonian cycle if and only if F is satisfiable. So somehow I have to get a notion of variables going in my graph, right? One thing you could think is like, maybe I could introduce a vertex, and then like if the Hamiltonian cycle visits that vertex, that's like setting the variable to true. And if it doesn't visit it, it's like setting the variable to false. Problem is the Hamiltonian cycle has to visit everything. So that's not going to work, right? So the idea is a bit more clever than that. It's instead, I'm going to create a chain of vertices which in the reduction they call a gadget. It's just like a line of vertices. And if I traverse that line, there's in any solution, there's only going to be two ways to traverse those vertices. Either I go from left to right or vice versa. I go from right to left. And if I go one way, it's like setting the variable that that gadget represents to true. And if I go the other way, it's like setting that variable to false. That's going to be the idea. Like, why am I doing a chain and stuff like that? I'll try to make that clear as we build up this reduction. But the idea is for each variable xi, we create a gadget. And a gadget looks like this. It's just a bunch of vertices in a row connected to their neighbors, like that, and then connected going backward as well. And I'm gonna like control the way these things are connected together so that the only way to visit all the vertices in it is going to be to traverse the whole chain going from left to right or from right to left. So if I go from right to left, I'm going to say that I set the corresponding variable xi to true. And if I go from left to right, I'm going to say I set it to false. So if we traverse the gadget from left to right, the variable is set to false. If we traverse the gadget from right to left, the variable is set to true. How long I make the gadget is going to depend on how many clauses that variable appears in. So let me show you how I'm going to connect it up, because somehow I have to, this maybe is a way to encode setting a variable to true or false, but somehow I have to connect it up to like clauses to decide whether I'm setting a clause, like whether I'm satisfying a clause, right? So that part's entirely unclear. So next we create a vertex for each clause. And then I connect the vertices for the clauses up to the gadgets for their corresponding variables. Okay, so how does that look? Let me draw a picture again. So connect it to the gadget for each variable in the clause. So as an example, let's say that I take the two clauses from my example. So Z1 is not X1 or X2 or X3, and Z2 was the second clause. It was X1 or X3. I think this is actually different than the one I wrote above. I don't know why. Anyway, those are two clauses. So now I create a gadget for X1. Like this. Okay, and I create X1 appears in both clauses, right? So now I create a vertex for clause Z1 and a vertex for clause Z2. If you remember, if I traverse my gadget going from left to right, that's like setting my that's like setting to false, right? Setting X1 to false. And if I traverse it this way, it's like setting it to true. So what I'm going to do is if I'm going, so let's look at Z1. X1 appears negated in Z1, right? Like not X1 is appearing there. So if I'm going across X1 in the false direction, I'm going to let myself go and visit Z1 because I'm satisfying Z1 by setting X1 to false. If instead I traverse X1 in the true direction from right to left, then since X1 appears with the positive literal in Z2, I get to visit Z2. So I'm going to connect up the clauses to the variables so that I get to visit them if I go in the direction that would satisfy that clause. So what I'm going to do then is to visit Z1. Oh, something like this. I could go down this way and back up to this one. And for Z2, right, I get to satisfy Z2 if I set X1 to true, which means traversing it from right to left. So it would be like this. And I make my gadget long enough so that I can connect up all these things without, like, I don't want to reuse a vertex for two of them. Do you know what I mean? Like, see how I connected this one to, I have an end vertex, then I connect Z1 to, 1 and 2. And then I connect Z2 to 3 and 4. And then I have another end vertex. So I'm going to make my chain long enough so I can have a free one on either end. And then I can connect my clauses such that there's no like overlap in the edges or in the vertices they connect to. That'll just help to ensure, it's like for flow control. I want to make sure there's no way that the Hamiltonian cycle solver can cheat and like visit clause variables without actually properly traversing my gadget. You know what I mean? Like, because I'm trying to enforce that when I find this Hamiltonian cycle, I can pull out the solution to SAT. Yeah. Yes, so I connected Z1 going left to right because not X1 appears in that clause. And that's the false direction. So I connected it in the false direction if it appears negated in the clause. And I connect it in the true direction if it appears not negated, right, as the positive literal. So, like I said, this is super complicated. It's complicated, but I think we can follow like what's going on at a high level, at least, So connect in true direction if xi appears in zj, and connect in the false direction if not xi appears in zj. And notice, like, a variable can never appear twice in a clause. It can't appear both positive and negative. If it did, you could just remove it, right? That one can't. Or sorry, if it appeared both positive and negative, then like no matter what you assign to that variable, you would satisfy the clause, right? And so we don't even need that clause. It's like a trivial clause. So you can just remove it from your problem. So now I need to connect up all my gadgets, right? I've got one for each variable. I've got a node for each clause, and now I need to connect them all up so that I can then compute a Hamiltonian cycle. And so the idea for connecting up the gadgets looks like this. So I have a start. Then I have my gadget for x1. Then I have my gadget for x2 below it. Goes down. I have my gadget for my last variable. And then I have t down here. And the edges that I add, basically any tour, it's going to go start at S, then it's going to traverse x1 in either the true direction or the false direction. Then it's going to traverse x2 in either the true or the false, and so on. It's just going to go down sequentially through my gadgets. So I'm going to connect it up like this. It goes from the start, I can either go to the false end or the true end. Then from whichever endpoint I leave, I can go to either endpoint of x2. So I need something that looks like this. I can go to there or to there. Like that. Right? And then these leave. And then from there, I go into my endpoint T. And then I have one more edge that takes me from T back up to S. So my Hamiltonian cycle, kind of in this graph, it's going to start at S. It's going to traverse the gadget for X1 in either the true or the false direction. Then it's going to go to the gadget for 2. It's going to traverse it in the true or the false direction, and so on. Finally traverse the gadget for Xn, and then go to T, and then come back around, back up to S. And the whole point is that the only way to get a Hamiltonian cycle in this graph, like to get a Hamiltonian cycle, I have to visit all the clause vertices, right? The Z1, Z2. And the only way to visit those is to traverse the corresponding gadget in the proper direction. You know what I mean? Like I only get to satisfy Z1 if I traverse X1 in the false direction, right? Or I traverse X2 in the true direction, or X3 in the true direction, whatever appeared in that clause. Yeah. Yeah. Three and it would be fine to go any way. Yeah, the ordering of them doesn't matter. Like I could have connected. That's a good question. So the question was just, is there a reason I connected up Z1 first, kind of on the clause, and then Z2 or on the gadget, and then Z2 after? There is not. The only requirement is that I don't like overlap my edges when I connect them up. Yeah. I think that's a good question. I think you need to connect them up to successive nodes like this, one after the other. And then like, the only thing I get worried about is like, you have to make sure you can't do any funny flow that's not allowed, where, for example, you go, let's say I connected up Z1 to this one, and then this one. And maybe I could go like down to it, then up, then I take this edge back, and then I go like to Z2, and then I go, like somehow I cheat the system with my path is able to cheat the system, you know, like, yeah. Yeah, you need 2 vertices for each clause and then 2 endpoints. Like each clause that the clause only has 1 vertex. It just gets connected up to all the gadgets. But what I was just saying is the length of a gadget is going to be 2 times the number of clauses that a variable appears in, plus the 2 endpoints. There won't be a way to skip between them. Maybe when I draw the final example, it'll be like kind of clearer why with this construction you can't cheat it. But it's exactly the right concern, right? Is like, I'm trying to set up all these rules for the flow so that things obey. Yeah. Yeah. I think what will happen, right, is you go across, like let's say you go down to Z1, and now you go out of Z1 to another gadget. You'll never be able to get back to this point on the gadget that you left. Like so you'll end up leaving some vertices unvisited. But this is the construction. And so what we do, basically start at S, travel each gadget in the true or the false direction, visit the clause vertices connected in the direction you're traversing that haven't been visited yet, right? The Hamiltonian cycle can't visit something twice. So the first variable that satisfies the clause gets to visit it, and all the other ones skip it. Once you finish traversing the gadget for Xn, go to T and then back to S. And the correctness of this, so I'm only going to give a hand wavy version of it because the things that everyone is worrying about are exactly, if you want to do it very precisely, you really have to try and prove that there's no way a Hamiltonian cycle could do anything other than what I want it to do, which is traverse complete gadgets before going to the next one. Like it can't somehow skip through clause nodes and get to another gadget and then skip through some more and get back somehow. And, you know, and I'm not going to go through that formally. But a Hamiltonian cycle on this graph gives a truth assignment for SAT. You just look at the direction of each gadget, and that tells you the true-false assignment. And if no truth assignment exists, then there's going to be no way to visit every clause. And that's the one that I think you have to dig into deeper if you want to do that proof formally. The other thing is that the size of the graph is polynomial in the length of the formula. Because each gadget has length equal to 2 times number of clauses it appears in plus 2 for the endpoints. And so it actually grows with like formula has a length, like the total number of variables appearing in the formula is length capital N, then the graph has big O of N vertices. The constant in front is something like 3. You create 2 copies, right? Like because you have to do, the gadget has 2 vertices for each time that variable appears. Then you get the endpoints, so that adds another couple, and then you have to add 1 vertex for each clause, right? And the clause number of clauses is less than or equal to capital N. So you just get several copies of the length N. So by the way, this reduction that I'm giving you, right, is one that like appeared in a paper that's very well cited from like, I think maybe it was the early 80s or mid 80s that someone proposed this. But like, you know, it was probably took them months to come up with and get it right, you know, and like, I mean, who knows? I've never talked to them, but like, this isn't something you're going to cook up really quickly, right? This idea, somehow you're trying to control all the flow of the Hamiltonian cycles so that they only traverse gadgets as you want them to. But it kind of shows how you can start to try and use this idea of reduction to relate very different problems. And so that's really all I wanted to emphasize in this. So let me take a few minutes to sketch out an example, because I think it'll kind of help. It'll also show you how ugly this idea becomes. So let's take a very simple formula, which is x1 or x2 and not x2, or not x3. And so this is the clause Z1, this is the clause Z2. So my reduction, I create a vertex S, then I create my gadget for x1. X1 appears in only 1 clause, right? So I just have to make the gadget length 4, the 2 endpoints, plus 2 vertices to connect up the clause. So it's going to be 1, 2, 3, 4. I like that. It's going to connect up to Z1 in the true direction because X1 appears non-negated in Z1. Then I have my gadget for X2. X2 appears in both clauses, right? So I need to create 4 vertices for the 2 appearances plus the endpoints, so a length 6 chain. Like that. It connects up to Z1 in the false or in the true direction as well, like that. And it also connects up to Z2 in the false direction. So it should go this way. And then I have X3. It appears once, so it's going to have a chain of length 4. 1, 2, 3, 4. And it connects up to Z2 in the false direction, which is this way. And then down here, I have my vertex T. So here, let me just draw this direction to remind you is false. This direction is true. I have to draw all my edges connecting everything. So I've got this one going back up to here. Then from S, I can go down to either side. And then I have to draw these cross ones too, right? Which are really going to screw up my, my drawing. Like that. And now in this mess, I compute a directed Hamiltonian cycle. And I think one option is that I go this way. I am going to traverse X1 in the true direction, because in doing that, I'm going to set Z1 to true. So I go along here, then I go down, back up, and across. X2, I'm going to traverse in the false direction. So I go down to this, then across. And then actually, I've already satisfied the both Z1 and Z2. So now I can traverse X3 in either direction. To make my picture a little simpler, I guess I'm just going to go this way. Like that. Then I go down to T and then travel back up around to S. Okay. So definitely a little bit wild, I understand. The last thing I wanted to fill in, but maybe I'll do it tomorrow, is just that directed Hamiltonian cycle can be reduced to undirected Hamiltonian cycle, the one we gave before. That's a simple reduction again, or fairly simple. This one, just for illustration purposes, to show you how kind of involved these things can get. One thing I've wanted to do, or I guess the last thing, is the course evaluations are available. And so I think I'll give you 10 minutes now. And they say, even though it's all done online, it's not with paper, they say that I should give you 10 minutes to fill it out. So let me put up I loaded this thing. They changed the name. It used to be evaluate. Now it's perceptions. I don't know. But I'm going to stop recording.